Hi, welcome to one more video on digital to analog converters. So in the previous videos we have seen binary weighted R and binary weighted C DAC circuits. So this is just the summary of those two circuits. So here we have considered a binary weighted R DAC with 4 bits. As you can see here, the weight of the resistance is varied as per the binary weight. Here it is 2R, 4R, 8R and 16R. Here you can observe one thing. If you are considering that bit to be 1, so that will be connected to the reference. If that bit is 0, it will be actually going to open circuit. So if it is 1, it is going to be reference, otherwise it is open circuit. The expression for the output voltage is given by this expression, and if you can see here, the output voltage is depending on the position of the bit. So if the bit is in P1, which is the MSB position, we will have half of the V reference voltage, and of course multiplied by the gain factor. If it is the LSB, then it is 1 by 16th, because we have 4 bit. So this way we will going to get the output voltage which is as per the binary weight of the input digital signal. So here as we discussed in the detailed class, so it is very difficult to realize resistors of different value on a VLSI. It is not so easy, and of course if the number of bits is keep on increasing, we know that after 16 it will become 32, then it is 64, then it is 128. So if the value of the resistance is not exactly those 2 power n, so then we may end up with errors which will lead to INL and DNL. So they thought of realizing these binary weighted values instead of resistors. They went to capacitors, because realization of capacitor is far more easier in VLSI circuits than the resistors. So this is what is the binary weighted C DAC circuit. This is again for 4 bit. So as we know that, okay, this is one of the capacitor which will be always grounded, will be equal to the least value of the capacitance in the bank here. So we start with C, then it is C by 2, C by 4, C by 8. So these are 4 bits. The last capacitance will be the replica of the last, whatever the last bit you have, that is B4 LSB bit. And here one thing to observe here is that if it is bit 1, it will be going to V reference. If it is bit 0, it will be going to ground. So whereas in case of binary R, if it was bit 0, it was going to open circuit, but here when bit is 0, so we are actually grounding the this particular switch. So the output expression is given by V reference, because we have a unity gain amplifier, that is a voltage follower. So that's why we have no gain for this particular circuit. The output voltage again as per the binary weight. So we have actually discussed this in detail in the previous video. How do we get it as B1 by 2 and B2 by 4 and B3 by 8 and B4 by 16. So this way we can able to get output voltage which is analog voltage, which is equal to the digital equivalent of the input voltage. So in both the cases, you can see here the resistance is varying as per 2 power n. Here the capacitance is keep reducing as per 2 power n. In both the cases, you cannot go for larger number of bits. Suppose assume that if the number of bits are like, okay, 10, 15, 12 or maybe 20 bits, then the reduction will be 2 power n minus 1. Here the increment will be 2 power n minus 1 here. So that is not a good sign for having large number of bits for the digital input. So then they realized instead of having these type of different values of resistance, is it possible to have only 2 resistance values, so that you can still realize a DAC circuit. So then they came up with DAC circuit using R2r circuit. So this is R2r circuit for realization of the DAC. So in this particular circuit, so we have the circuit going like this. We have a resistor 2R which is grounded all the time. Then I have one more resistor 2R. This is R, then it is 2R, To start with, let us consider only 2 bits over here. So let me again consider this is the switch now. Okay, let me consider these two are the switch positions, and let me consider this as a non-inverting input to the non-inverting amplifier. This is plus minus. Let me consider this as the amplifier gain R1 RF. So this is V0. So here I have again 2 possible positions. Let me consider this as one and this as the other one. So let me connect this to this, connect this to this, and let me connect this to this, and this is connected here. Let me connect this to ground. Let me ground this. Let me connect it to this is the reference. So here also this will be either 1 or 0. If it is 1, it will be going to, suppose if it is logic 1, it is V reference. If it is logic 0, it is the ground. So it is V reference and the ground, the 2 possible voltages for the bits here. So let me consider this as B1, this is B2, this I say it as MSB. Okay, let us consider the combination of B1, B2. So let me consider this as 1, 0. Whenever I consider the MSB as 1, so this is 1 and this is 0. So when you say, okay, let me just rewrite, before that, okay, let us try to identify what is the output voltage. Is output voltage V0 is equal to, suppose if I say this as Vx, shall I say it as Vx into 1 plus Rf by R1? This is the expression for the output voltage. Let us try to understand what is Vx is when it is B1 is 1 and B2 is 0, and let us also consider when B2 is 1 and B1 is 0, what is the output voltage. So from which we can get the value of Vx. So for this particular thing, so I can rewrite the circuit diagram only this Vx part. So I can rewrite it as, this is already grounded, so this is 2R. Since you are considering B2 as 0, so this is also grounded, so I'll have this also 2R grounded, because when it is 0 it will be grounded. Then you have a resistor R, and then you have 2R. This is actually B2 is equal to 0, B1 is equal to 1. 1 means it is now V reference. V reference, you are looking at what is this Vx is. If you can see here, if you look from this side, is it 2R coming in parallel? Since 2R and coming in parallel, it will end up with the effective resistance of, R, that is grounded. So then you have a R and R coming in series, so that will become 2R. So that 2R and this 2R, so they are in series now. That is, this is 2R and you are going to have one more 2R here which connected to ground. So then this Vx happens to be, because you have two resistance 2R and one more 2R which is grounded, so does this becomes V reference by 2. The voltage here Vx becomes half of the V reference voltage, because you have one 2R here and one more resistor R and another effective resistance R. They will in total become 2R. The effective circuit looks something like this. You have, this is effectively grounded. If you are looking at Vx, this is 2R, this is also 2R, you have V reference. So in such case, the Vx voltage will becomes half of V reference, which is half of V reference. So if I write what is V0 is, so when B1 and B2 it is 1, 0, do I have output voltage as equal to Vx into 1 plus Rf by R1 is equal to, is Vx is equal to Vref by 2. So this is for this particular combination is 1 plus Rf by R1. Suppose I say this as R1, this as R1. So similarly, let us see, if I have B1 as 0 and B2 as 1, how does the equivalent circuit looks like? So does the equivalent circuit look like this? So if you just come back here, so this will be connected to the reference, this will be connected to ground, and you have this as R. So I have a combination, or I have the equivalent circuit. This is now 2R, and I have a 2R here. There is a V reference connected, and you have a R, and you have a 2R, and this is what you're looking at, Vx. So now, since you have a V reference here, so I need to find out what is the voltage looking from here, what is V Thevenin and R Thevenin. So V Thevenin, R Thevenin looking into the circuit will be equal to, suppose find out what is V Thevenin. It's actually because you have V reference and two resistance of same value, is V Thevenin is equal to V reference by 2. And what is R Thevenin? So when you ground this and then see from here, this is grounded, this is grounded, you have 2R resistances coming in parallel. Does R Thevenin becomes equal to 2R in parallel with 2R will become just R. So I will end up with a circuit diagram equal to this would be looking like this. This is the circuit diagram. This is R Thevenin, this is V Thevenin, this is that R, and I have this is grounded, this is 2R. I am looking at what is Vx. But what is V Thevenin? This is actually to V reference by 2. What is R Thevenin? It is R. So do we have a circuit now which is having V reference by 2 as the voltage source, and you have total resistance of 2R there, because this is R plus R, and do I have one more 2R here? Are you looking at Vx? So if you can carefully look at what is the voltage of Vx, having a source of V reference by 2, does Vx is equal to V reference by 2 whole of 2? Is it actually V reference by 4? This is V reference by 4 when B2 is 1, when B2 is 1. So I can write the final expression for the output voltage for a general circuit, for a general R2r circuit, as equal to 1 plus Rf by R1 into Vref divided by, it is B1 by 2 plus B2 by 4. If you want to have it for n number, the circuit goes this way. So this is my 2R resistor always grounded. This is first 2R, this is R, then this is 2R, then this is again R, then this is 2R, then this is R, then you have 2R. This will go to the inverting terminal. You can have a resistor, or you can have a unity gain amplifier. Both can be possible. R1, Rf. Of course, as it was said, if it is 1, it will go to VCC. If it is 0, it will go to ground. So you have either V reference or ground. So let me just write the ground here. Let me write the ground. So this is ground here, and this is V reference. This is logic 1. This is for 1. This is for 0. If the pit is 0, it will come to ground. If the pit is 1, it will go to the reference. Now this is actually the bit B1, B2, B3 and B4. So B1 is actually MSB bit. So this is MSB bit. So if you want to write the expression over here, it is the same expression. You can write two more bits. It is B3 by 8 plus B4 by 16. So this is just an extension of two more bits to the earlier expression, because it is the same gain what you have. So it is 1 plus RF by R1, and the voltage at this point, now instead of only 2 bits you have 4 bits. So this is one such implementation of DAC circuit, which consists of only two sets of resistance, only R and 2R. Only the values of the resistance are R and 2R. Unlike in your previous case where the resistance was kept on varying from 2R, 4R, 8R, that is not there. It is only R and 2R. Irrespective of the number of bits you are going to have in your input, it will be only R and 2R. So here whatever you are getting is you will get a voltage Vx and then multiplied by the gain of the amplifier. So let us see one more circuit where we have almost a similar type of analysis, but let us see what is the one more implementation of R2r. This is again R2r DAC circuit. So let me just rewrite the same circuit here. So I have a circuit, so as I had it here, let me start with this is my first resistor 2R, this is again 2R, then I'll have a resistor R, this is 2R, then I'll have, okay, let me consider only 2 bits for the time being. Let me have a resistor, let me have a voltage source, V reference, and let me, okay, before this we will have a general network, which is something like this here. So this is a very general network. So let me have this type of network. This is some Vx, this is R, this is 2R, again 2R, this is R, this is R, this is 2R, this is 2R, this is 2R, it's grounded. Suppose if you see from this side, if you see from here, okay, if you see from here, what is the effective resistance? Can you see this, since it is grounded, this 2R come in parallel, and that 2R coming in series, will it become effective resistance of 2R? No, you have an effective resistance 2R, that 2R come in parallel with this 2R, it will become R, that R plus this R will become again 2R. So from this point, if you see, it's again this effective resistance 2R, that 2R coming in parallel with 2R will become R, that R plus this R is equal to R, so this is 2R. So the point now what we are looking at is, if this is Vx, how much is the current that may flow here? Let me say this as some I1, let me say this as I2, let me say this as I3, let me say this as I4. I am interested in knowing what is I1, I2, I3 and I4. Let me say the voltages at this point as equal to V1, V2, V3, V4. Shall I say this as V1, because whatever I1 I am saying, is it actually V1 by 2R? I will write it as V1 by 2R. What is the voltage I2? Is it actually V2 by 2R? So it's again now V2 by 2R. So what is I3? It's V3 by 2R. It is V3 by 2R. Now it is finally V4 by 2R. Now the point is, what is V1 in terms of Vx? So is V1 is equal to Vx? Because it is the same voltage going there, it's actually coming out to be Vx by 2R. Now what is the voltage at this point in terms of Vx. We know that this is R. This is R. So what is suppose if this is suppose if this voltage is Vx. So do we have something like you have a voltage Vx here, you have a resistance R here, this is a resistance R. Looking from here, what is the effective resistance? Now can you say this is R and R, 2R coming in parallel will become R, and then that in series which will become 2R. And if you see here, is the resistance looking towards this is 2R, that 2R coming in parallel with this 2R, will it become R? So is the resistance looking from here, is it equal to R here? From here it is 2R. So if you look at this point, is it actually only R? So I have a resistance Vx here. So you have a equivalent. Okay, I want to know what is voltage Vx. It's actually you have a Vx voltage here, and you have a resistor R, and you have an effective resistance R here. So I can just simply write this as you have a Vx, you have a resistor R, and you have an equivalent resistor R which is grounded here. You are looking at what is V2 is. Is V2 is equal to Vx by 2? Is V2 is equal to Vx by 2? So shall I write it as Vx by 4R? Similarly, can I write it as Vx by 8R? Because the voltage at V3 will become Vx by 4, and voltage at V4 will become Vx by 8, as on the same lines. Here it is Vx by 2, Vx by 4, Vx by 8. So the effective current that is flowing through each of the resistors is Vx by 2R, Vx by 8R, Vx by 4R, and finally here it is Vx by 16R. So let us utilize this concept and try to understand how it can be used for TAC application. So here we have a circuit something like this here. Let me say this is minus, plus, and let me also consider a resistor R here. I have this, and this is grounded. Okay, let me have two terminals. One is for, this is for 1, this is for 0, this is for 1, this is for 0. I have the switch. If it is 1, let it go here. If it is 1, let it go here. If it is 0, let it go here. If it is 0, it's going here. Now, so let us try to understand this current I1, this current I2. So looking at this, if it is 1, is the current I1 is going to inverting terminal? Here, if this is actually a bit, this is B1, this is B2. If B1 is equal to 1, the switch is connected here. Whatever current that is flowing here, so what is the current that is going to flow here? Is it actually I1 is equal to V reference by 2R, so as we had it here. Then what is I2 current? I2 current is equal to, here what is the voltage? Here it's actually equal to V reference by 2 divided by 2R. So that will become V reference by 4R. So this is actually the current that is going to flow over here. So this is when only B1 is equal to 1. This is when only B2 is equal to 1. If B1, B2 both are 1, then depending on the condition of whether B1 is 1 or 0, so I will have the current, the summation of all these things. So I can write the current I0 as equal to B1 V reference by 2R plus B2 V reference by 4R. So what is this possible values of B1, B2? It can be 1 or 0. If it is 0, 0, no current flows here. But the entire current will flow through this I0 bar. That is because we know that the current will either go through this line or it will go through the other line, because it can be either 1 or 0. If it is 0, the same current will flow here. If it is 1, then only the current will go to the inverting terminal, of course, which is in turn goes here. So at any point of time, the current will either go to ground or it will go to inverting terminal. When I say inverting terminal, it will go through R. So of course, when I say inverting terminal, the current actually goes here, which in turn goes through resistor R. So now, what is the output expression? Shall I say output expression V0 is equal to minus I0 into R? When it is minus I0 into R, shall I write it as, so minus of I0 is nothing but this. So shall I write it as R V reference by R into B1 by 2 plus B2 by 4. This R and R will go off. Will it become minus V reference multiplied by B1 by 2 plus B2 by 4? Meaning, this is, of course, what is this I0? I'm just rewriting the same I0 here. So that is because whatever this is how the current is flowing. So what is V0? V0 is actually equal to the drop, that is negative the drop here. So because the current is flowing in this direction, so V0 is actually equal to minus of I0 by R. So why I0 by R is because no current will flow here. This is zero current, the entire current will flow here. The V0 is actually equal to plus minus. So of course minus means this is virtual ground. So V0 is equal to this is actually I0. So V0 is actually equal to minus I0 into R. So I'm trying to take out this V reference outside, and of course R is there as a product. So it is V reference multiplied by R divided by R into the binary weight of the input voltage. So this way we can able to realize this R2r DAC using one more mode. This is called as current mode R2r network. Why it is called as current mode R2r network is because you are considering the current that is going to flow here. So this way we can able to realize the R2r network in two different ways. One is called as current mode DAC R2r. On contrary, this is actually called as voltage mode. This is voltage mode R2r, because whatever you're getting is Vx is voltage, that Vx multiplied by the gain of the amplifier will become voltage mode R2r DAC. Okay, we will see more of this current mode circuit in the next video.